In this video, I'm going to describe some of the things that make it difficult to recognize objects in real scenes. We're incredibly good at this, and so it's very hard for us to realize how difficult it is to take a bunch of numbers that describe the intensities of pixels and go from there to the label of an object. There's all sorts of difficulties. We have to segment the object out. We have to deal with variations in lighting, in viewpoint. We have to deal with the fact that the definitions of objects are quite complicated. It's also possible that to get from an image to an object requires huge amounts of knowledge, even for the lower level processes that involve segmentation and dealing with viewpoint and lighting. If that's the case, it's going to be very hard for any hand-engineered program to be able to do a good job of those things. There are many reasons why it's hard to recognize objects in images. First of all, it's hard to segment out an object from the other things in an image. In the real world we move around, and so we have motion cues. We also have two eyes, so we have stereo cues. You don't get those in static images. So it's very hard to tell which pieces go together as parts of the same object. Also, parts of an object can be hidden behind other objects, and so you often don't see the whole of an object. You're so good at doing vision that you don't often notice this. Another thing that makes it very hard to recognize objects is that the intensity of a pixel is determined as much by the lighting as it is by the nature of the object. So, for example, a black surface in bright light will give you much more intense pixels than a white surface in very gloomy light. Remember, to recognize an object, you've got to convert a bunch of numbers, that is the intensities of the pixels, into a class label. And these intensities are varying for all sorts of reasons that are nothing to do with the nature of the object, or nothing to do with the identity of the object. Objects can also deform in a variety of ways. So for relatively simple things, like handwritten digits, there's a wide variety of different shapes that have the same name. A 2, for example, could be very italic with just a cusp instead of a loop. Or it could be a very loopy 2 with a big loop and very round. It's also the case that for many types of object, the class is defined more by what the object's for than by its visual appearance. So consider chairs. There's a huge variety of things we call chairs, from armchairs to modern chairs made with steel frames and wood backs, to basically anything you can sit on. One other thing that makes it hard to recognize objects is that we have different viewpoints. So there's a wide variety of viewpoints from which we can recognize a 3D object. Now, changes in viewpoint cause changes in the images that standard machine learning methods cannot cope with. The problem is that information hops about between the input dimensions. So typically envision the input dimensions correspond to pixels, and if an object moves in the world and you don't move your eyes to follow it, the information about the object will occur on different pixels. That's not the kind of thing we normally have to deal with in machine learning. Just to stress that point, suppose we had a medical database in which one of the inputs is the age of a patient and another input is the weight of the patient. And we start doing machine learning, and then we realize that some coder has actually changed which input dimension is coding which property. So for one of the coders, they've put weight where they should have put age, and they put age where they should have put weight. Obviously, we wouldn't just carry on doing our learning. We'd try and do something to fix that. That's going to make everything go wrong. I call that phenomenon dimension hopping, when information jumps from one input dimension to another. And that's what Viewpoint does, and it's something we need to fix. And preferably, we'd like to fix it in a systematic way. In this video, I'm going to talk about the issue of viewpoint invariance. Each time we look at an object in a scene, we typically have a different viewpoint, so the object shows up on different pixels. This makes object recognition very unlike most machine learning tasks. and I'm going to talk about various ways of trying to deal with that issue. A number of different ways have been suggested for coping with viewpoint variations. We're so good at it that we don't really appreciate how difficult it is. It's one of the main difficulties in making computers perceive, and there still aren't generally accepted solutions, either in engineering or in psychology. The first approach is to use redundant invariant features. The second approach is to put a box around the object so that you can normalize the pixels. The third approach is to use replicated features and pool them. This is called convolutional neural nets, and I'll go over that in great detail. And the fourth approach, which I'll talk about at the end of the lecture, is to use a hierarchy of parts and to explicitly represent the poses of the parts relative to the camera or retina. So, the invariant feature approach says you should extract a large and redundant set of features, and they should be features that are invariant under the transformations like translation and rotation and scaling. So here's an example of an invariant feature. It's a pair of roughly parallel lines with a red dot between them. That's actually been suggested as the feature that baby herring gulls use for knowing where to peck for food. If you paint that feature on a piece of wood, they'll peck at the appropriate place on the piece of wood. With enough invariant features, there's only one way to assemble them into an object or an image. You don't actually need to represent the relationships between features directly, because those relationships are captured by other features. This has been pointed out for strings of letters by a psychologist called Wayne Wickelgren. It's been pointed out in vision by Shimon Ullman, and it's a sort of cute point that all we need is a big bag of features, because with overlapping and redundant features, one feature will tell you how two other features are related. Unfortunately, if you're doing recognition, you're going to get a whole bunch of features that are composed of parts of different objects, and they'll be very misleading for recognition. So you'd like to avoid forming features from parts of different objects. A second approach is what I call judicious normalization. So if you look at that upside down capital letter R on the right, I've put a box around it, not very well in fact, and I've labelled a top and a front for that box. And relative to that box, the R has, for example, a vertical stroke at the back, and it has a loop facing forwards at the top. So if we describe features of the R relative to that box, they're going to be invariant. This is assuming it's a rigid shape. Putting a box around a rigid shape solves the dimension hopping problem. It gets rid of the effect of changes in viewpoint. If we choose the box correctly, the same part of an object would always occur on the same normalized pixels. It doesn't have to be a rectangular box. We can provide invariance to not only translation and rotation and scale, but also things like shear and stretch. Unfortunately, choosing the box is difficult. It's difficult because we might have segmentation errors, we might have occlusion, so you can't just shrink a box around things. We might have unusual orientations. That example of the upside down R makes it clear that we have to use our knowledge of what the shape is to help us decide what the box is. If, for example, we had a character that was like a lowercase d, but with an extra stroke coming out of the loop of the d, we would see that as an upright one of those characters. So it's a chicken and egg problem. In order to get the box right, we need to recognize the shape, and in order to recognize the shape, we need to get the box right. An aside here for psychologists. Many psychologists think we do mental rotation to deal with shapes that aren't oriented right. This is complete nonsense. That capital letter R you recognize perfectly well before you do any mental rotation. Indeed, you need to recognize that it is an R and it's upside down in order to know how to rotate it. You use mental rotation for dealing with judgments like handedness, that is it a correct R or a mirror image R? You can't tell that without doing mental rotation. But mental rotation is not used for dealing with the fact that it's upside down when we want to recognize it. The brute force normalization approach works like this. You use well-segmented upright images that you can judiciously put a box round when you train the recognizer, and then at test time, when you have to deal with cluttered images, you try all possible boxes in a whole range of positions and scales. This approach is widely used in computer vision, particularly for detecting upright things like faces or house numbers in unsegmented images. It's much more efficient if the recognizer can cope with some variation in the position and scale, so that we can use a coarse grid when trying all possible boxes. In this video, I'm going to talk about convolutional neural networks for handwritten digit recognition. This was one of the big success stories of neural networks in the 1980s. The deep convolutional nets developed by Yann LeCun and his collaborators did a really good job of recognizing handwriting and were actually used in practice. They're one of the few examples from that period of deep neural nets that it was possible to train on computers that existed then and that performed really well. Convolutional neural networks are based on the idea of replicated features. So because objects move around and show up on different pixels, if we have a feature detector that's useful in one place in the image, it's likely that the same feature detector will be useful somewhere else. So the idea is to build many different copies of the same feature detector in all the different positions. If you look on the right, I've shown you 3 feature detectors which are replicas of each other. Each of them has weights to 9 pixels, and those weights are identical between the 3 different feature detectors. So the red arrow has the same weight on it for all 3 feature detectors. And when we learn, we keep those red arrows all having the same weight as each other, and we keep the green arrows all having the same weight as each other, even though the red and green arrows will have different weights. We could also try replicating across scale and orientation, but that's much more difficult and expensive, and probably not a good idea. Replication across position greatly reduces the number of free parameters that you have to learn. So those 27 pixels that you see in those 3 replicated detectors only have 9 different weights. Now, we don't just want to use one feature type, so we're going to have many maps. Each map will have replicas of the same feature, features that are constrained to be identical in different places, and then different maps will learn to detect different features. This allows each patch of the image to be represented by features of many different types. Replicated features fit in nicely with backpropagation. That is, it's easy to learn them using backpropagation. In fact, it's easy to modify the backpropagation algorithm to incorporate any kind of linear constraint between the weights. So what we do is we compute the gradients as usual, but then we modify the gradients so that if the weights satisfied the linear constraint before the weight update, they'll also satisfy the linear constraint after the weight update. So the simplest example is we want 2 weights to be equal. We want W1 to equal W2. That'll be true if we start off with W1 equal to W2, and then we make sure that the change in W1 is always equal to the change in W2. The way we do that is we compute the gradient of the error with respect to W1 and the gradient with respect to W2, and then we use the sum or average of those 2 gradients for both W1 and W2. By using weight constraints like that, we can force backpropagation to learn replicated feature detectors. There's quite a lot of confusion in the literature about what replicated feature detectors are actually achieving. Many people claim they're achieving translation invariance, and that's not true. Well, at least it's not true in the activities of the neurons. So if you look at the activities, what replicated features achieve is equivariance, not invariance. An example should make that clear. Here's an image, and the black dots are the activated neurons. Here's a translated image, and notice the black dots have also translated. So the image changed, and the representation also changed by just as much as the image. That's equivariance, not invariance. There is something that's invariant, and that's the knowledge. So if you learn replicated feature detectors, if you know how to detect a feature in one place, you'll know how to detect that same feature in another place. And it's important to note that we're achieving equivariance in the activities and invariance in the weights. If you want to achieve some invariance in the activities, what you need to do is pool the outputs of replicated feature detectors. So you can get a small amount of translational invariance at each level of a deep net by averaging 4 neighbouring replicated detectors. One advantage of this is that it reduces the number of inputs to the next layer so that we can have more different maps, allowing us to learn more different kinds of features in the next layer. It actually works slightly better to take the maximum of 4 neighbouring feature detectors rather than an average. But there is a problem, and the problem is that after several levels of doing this kind of pooling, we've lost precise information about where things are. That's okay if we just want to recognise that there's a face. The fact that we've got a few eyes and a nose and a mouth floating about in vaguely the same position is very good evidence that it's a face. But if you want to recognise whose face it is, you need to use the precise spatial relationships between the eyes and between the nose and the mouth, and that's been lost by these convolutional neural nets. I'll come back to that issue later on. So the first impressive example of a convolutional neural net was done by Yann LeCun and his collaborators, who developed a really good recognizer for handwritten digits. Their net had many hidden layers. In each layer it had many maps of replicated units, and it had pooling between layers, so you pool adjacent replicated units before you send them to the next layer. They also used a wide net that could cope with several characters at once, and that would work even if the characters overlapped, so you didn't have to segment out individual characters before you fed them to their net. And something which people often forget is that they used a clever way of training a complete system. They weren't just training a recognizer for individual characters. They were training a complete system so that you'd put in pixels at one end and you get out whole zip codes at the other end. And in training that system, they used a method that would now be called maximum margin, but when they did it, it was way before maximum margin had been invented. The net they used was at one point responsible for reading about 10% of the checks in North America, so it was a great practical value. There's very nice demos of the net on Yann's webpage, and you really should go and look at those, look at all of them, because they show you just how well it copes with variations in size, orientation, position, overlap of digits, and all sorts of background noise that would kill most methods. The architecture of the Net 5 looks like this. There's an input, which is pixels, and then there's a whole sequence of feature maps followed by subsampling. So in the C1 feature map, there's 6 different maps, each of which is 28 by 28, and those maps contain small features that just look at, I think, 3 by 3 pixels, and their weights are constrained together. So per map, there's only about 9 parameters. That makes learning much more efficient and means you need much less data. Then after the feature map, there's what they call subsampling, which is now called pooling, and so you pool together the outputs of a bunch of neighbouring replicated features in C1, and that gives you a smaller map which will then provide the input to the next layer, which is discovering more complicated replicated features. As you go up this hierarchy, you get features that are much more complicated but are more invariant to position. Here's the errors that LeNet 5 made, and this shows you that the data it's dealing with is quite tricky. There's 10,000 test cases, and these are the 82 errors it makes, so it's doing better than 99% correct. Nevertheless, most of the errors it makes are things people find quite easy to recognize, so there's some way to go still. Nobody knows the human error rate on this data, but it's probably 20 to 30 errors. Of course, there might be digits that LeNet 5 got right and you would get wrong. So you have to be careful in estimating the error rate. You can't just look at these 82 and ask which ones you get right and which ones you get wrong. You have to worry about all those other ones that LeNet 5 might have got right and you might have got wrong. I now want to go to a very general point about how to inject prior knowledge in machine learning, and it applies particularly to neural networks. We can put in prior knowledge, as is done in LeNet 5, by the design of the network. We can have local connectivity, we can have weight constraints, or we can choose neural activities that are particularly appropriate for the task we're doing. This is much less intrusive than trying to hand engineer the features, but it still prejudices the network towards a particular way of solving the problem that we had in mind. We have an idea about how to do object recognition by gradually making bigger and bigger features and by replicating these features across space, and we force the network to do it that way. There is an alternative way to put in prior knowledge that gives the network a much freer hand. What we can do is use our prior knowledge to create a whole lot more training data. One of the first examples of this was work by Hoffman and Tresp on trying to model what happens in a steel mill. They wanted to know the relationship between what comes out of the steel mill and various input variables, and they actually had a big old Fortran simulator that would allow them to simulate the steel mill. Of course, the simulator wasn't reality, it was making all sorts of approximations. So they had real data and also a simulator. And what they did was ran the simulator in order to create some synthetic data. They then added that to the real data and showed that they could do better than just using the real data alone. If I remember right, their great big Fortran simulator was only worth a few dozen extra real examples, but nevertheless they made the point. Of course, if you generate a lot of synthetic data, it may make learning take much longer. So in terms of the speed of learning, it's much more efficient to put in knowledge by using things like connectivity and weight constraints, as was done in LeNet 5. But as computers get faster, this other way of putting in knowledge, by generating synthetic examples, begins to look better and better. In particular, it allows optimization to discover clever ways of using the multilayer network that we didn't think of. In fact, we might never fully understand how it does it. If we just want good solutions to a problem, that might be fine. So, using the idea of synthetic data, there's a brute force approach to handwritten digit recognition. LeNet 5 uses knowledge about invariances to design the connectivity and the weight sharing and the pooling, and that achieves about 80 errors. Adding a lot more tricks, including synthetic data, Marco Ranzato was able to get that down to about 40 errors. A group in Switzerland, led by Jürgen Schmidhuber, went to town with injecting knowledge by putting in synthetic data. They put a lot of work into creating very instructive synthetic data. So for every real training case, they transformed it to make many more training examples. They then trained a large net with many units per layer and many layers on a graphics processor unit. The graphics processor unit gave them a factor of 30 in computation, and because of all the synthetic data they put in, it didn't overfit. If they'd just used a large net with a GPU, it would have been a disaster. They'd have overfitted terribly. They'd have done perfectly on the training data, but terribly on the test data. So really they were combining three tricks. Put your effort into generating lots of synthetic data, then train a large dumb net on a GPU. They managed to achieve 35 errors like that. So here's the 35 errors they got. The top printed digit is the right answer, and the bottom two digits are their top two answers. What you'll notice is that they nearly always get the right answer in their top two. There's only 5 cases where they don't. With some more work, by building several different models like this and then using a consensus to decide what the digit was, they managed to get down to about 25 errors. And that must be around about the human error rate. One question this work raises is how do you tell if a model that makes 30 errors is really better than a model that makes 40 errors? Is that significantly different? Rather surprisingly, it turns out it depends on which errors they make. The numbers don't provide you enough information. You have to know which ones they get wrong and which ones they get right. So there's a statistical test called the McNemar test that uses the particular errors and is far more sensitive than just using the numbers. Let me give you an example. If you look at this 2x2 table, it shows you in the top left-hand corner how many examples Model 1 got wrong and Model 2 also got wrong. That's 29. And in the bottom right, it shows you how many examples Model 1 got right and Model 2 also got right. And in the McNemar test, you can just ignore those numbers in black. What you're interested in is the ones where Model 1 got it right and Model 2 get it wrong, or Model 2 got it right and Model 1 get it wrong. And if you look at that, there's an 11-to-1 ratio, and it turns out that's pretty significant. Model 2 is definitely better than Model 1. That didn't happen by accident, almost certainly. By contrast, if you look at this table, again, Model 1 is making 40 errors, and Model 2 is making 30 errors. But now, Model 1 is winning 15 times when Model 2 loses, and Model 2 is winning 25 times when Model 1 loses. That difference is not very significant, so we wouldn't be confident that Model 2 is better than Model 1. It was always a question for speculation whether the kinds of nets developed for recognising handwritten digits could actually be scaled up to what vision people call a real task, that is, recognising objects in high-resolution colour images when the scene is cluttered, so that you have to do things like segmentation, you have to deal with 3D viewpoint, you have to deal with the fact that there's many different objects around and you're not quite sure which is the intended one, and so on. Since the start of this course, we've got some interesting new results on that. So in my first lecture, I described the network developed by Geoffrey and showed that it was good at object recognition, but at that point it hadn't been benchmarked against the best computer vision systems. Now it has. People worked on MNIST for many years, gradually improving their ability of these networks to recognize handwritten digits. Many computer vision researchers thought this was a waste of time if you wanted to be able to recognize real objects in color images, because they thought that the lessons learned from MNIST would not generalize to that domain. That was a fairly reasonable thing to think. Here's a number of reasons why it's a much more difficult task. First of all, there's many more different kinds of objects. Even if we only recognize 1,000 classes, that's still a factor of 100. Secondly, there's many more pixels. Even if we use downsampled images that are only 256 by 256 with color pixels, that's still 100 or 300 times as many pixels. Another factor is that in real scenes you have to deal with the fact you've got a two-dimensional image of a three-dimensional reality, so a lot of information's been lost. And real scenes have clutter of a kind that doesn't occur in handwriting. In handwriting you can have overlapping letters, and that requires segmentation. But you don't have things like occlusion of large parts of objects by opaque other objects. You don't have many different kinds of object in the same scene. And you don't have all the lighting variations that you get in real scenes. So the question is, will the same kind of convolutional neural network that proved to be so good at recognizing handwritten digits work for real color images? In the domain of real color images, we probably do need to wire in some prior knowledge, because if we try and do it in the Sirisan way with no knowledge wired in, putting in all the knowledge by generating extra training examples, the computational problem is still too large for current computers. So there was a recent competition, and it was on a database called ImageNet. ImageNet actually has many more than 1 million images, but a subset of 1.2 million images was chosen, and the classification task was to correctly label those images. Now, the images were hand-labeled with 1,000 different classes, but this wasn't very reliable. there could be an image that has 2 of those 1,000 different objects in, and only one of them is labelled. So, to make the task feasible, the computer vision system is allowed to make 5 bets, and it's said to get it right if one of those bets corresponds to the label that a person has given the image. There's also a localization task. The reason for the localization task is that many computer vision systems use a bag of features approach. For the whole image, or for, say, a quadrant of the image, they know what the features are, but they don't know where they are. This allows them to recognize objects, but without knowing exactly where they are. That's very unlike how people behave, except people with a curious kind of brain damage called balance syndrome, where they can recognize objects and not be sure where they are. So for the localization task, you have to place a box around an object once you've recognized it, and to get it right, your box must have at least a 50% overlap with the correct box. On this task, people tried some of the best existing computer vision methods. So leading groups from Oxford and the French National Research Labs, INRIA, and Xerox's European Research Centre, and various other universities tried this task and discovered it's very hard. The computer vision systems typically use complicated multi-stage systems. The early stages of these systems are typically hand-tuned by optimizing a few parameters using some of the data, and the top stage of these systems is always a learning algorithm. But they don't learn all the way through in the way that a deep neural net does when it's trained with backpropagation. They don't have end-to-end learning, where the parameters used in the early feature detectors are being influenced by how useful they are for making the final decision about classes. So here's some examples from the test set to show you what the data's like. You already saw some examples in the first lecture, but here's some more. So you can see that it's fairly obvious what the object is in that image, but a lot of it's missing. It doesn't have ears, it doesn't have legs. The predictions are the unnormalized probabilities of Alex Krizhevsky's deep neural network, and you can see it's confident that that's a cheetah, and if it's not a cheetah, it thinks it's almost certainly a leopard. It also understands there's other possibilities like a snow leopard. It's the wrong colour for a snow leopard, or an Egyptian cat. Here's an example the other way around. Here there's many objects in the image, and the object of interest is only a very small fraction of the pixels. The network correctly says bullet train, but it also has other bets, like subway train or electric locomotive, which are pretty sensible bets. If you look at the image, there's lots of other things that could be labelled, like the roof, which occupies a much larger fraction of the image than the train, or the pillar that's supporting the roof, or the pedestrian, or the large apartment block in the background. In these kinds of images, you really have to be able to cope with the fact that there's lots of alternative targets. The last image shows a different kind of example, where there's no background clutter. The object is quite well isolated, probably a picture from a catalogue or something. And the network doesn't get it right for its first bet, but it does get it in its top 5 bets. But here the network isn't confident about anything. These are the relative probabilities. And the network correctly realizes it doesn't really know. And if you look at the other possibilities, they're all perfectly plausible. If you screw your eyes up so you can't see the image too well, you can see how it might think it was a frying pan or a stethoscope. So how did the systems do on this data? Here's the error rates for the computer vision systems. And one thing you'll notice is that the best systems are all very similar. So the University of Tokyo managed to get 26.1%. And here what I'm doing is just reporting the best system from each group. Oxford University, which has a very good computer vision group, generally recognised to be possibly the best group in Europe, again got in the 26%, and the French National Research Labs and the Xerox PARC Centre, which are, again, very good computer vision groups, got 27%. So you'd have guessed from this that it's going to be hard to beat 26%, and if you do beat 26%, you're comparable with the very best computer vision systems. So Alex Krizhevsky's neural net got 16% error. It's a huge gap. Normally in these competitions, you don't see big gaps like that. So Alex Krizhevsky's network works like this. It's a very deep convolutional neural net of the type pioneered by Yann LeCun that was first used for digit recognition, and then Jan later applied it to recognizing real objects. And we're using all the lessons that were learned by Jan's group and by Yoshua Bengio's group and by various other groups, developing these deep neural nets for doing real vision. It has 7 hidden layers, which is deeper than usual, and that's not counting some of the max pooling layers. The early layers are convolutional. We could probably get away with using just local receptive fields without tying any weights if we had a much bigger computer. But by making them convolutional, you cut down the number of parameters a lot, so you cut down the amount of training data you need a lot, which cuts down the amount of computation time a lot. The last 2 layers were globally connected, and that's where most of the parameters are. I think there's about 16 million parameters between each pair of those layers. What the last 2 layers are doing is looking for combinations of local features that were extracted by the early layers, and obviously there's combinatorially many combinations to look for, and that's why you need a lot of parameters there. The activation functions were rectified linear units in every hidden layer. These train much faster than logistic units, and they're more expressive. Most of the people seriously applying deep neural networks to real images to do object recognition have now switched to rectified linear units. We also used competitive normalization within a layer to suppress the activity of a unit if other units that are looking at nearby localities are very active. This helps a lot with variations in intensity. So you might have an edge detector which gets somewhat active due to some fairly faint edge, and that's pretty much irrelevant if there's much more intense things around. There's other tricks that we use to significantly improve the generalization of this net. First of all, we used the trick of enhancing the data by using transformations. So Ilias at Skiva downsampled the images in the competition to 256 by 256, but instead of using those whole images, Alex Krzyzewski took random 224 by 224 patches from those images, which gave him hugely more images to train on and helped him deal with translation invariance. Even though they're convolutional nets, that's still a help. He also used left-right reflections of the images, which again doubled the amount of data. He didn't use up-down reflections because gravity is very important. Left-right reflections don't really change what things look like much unless they're things like writing. At test time, he doesn't just use one patch. He uses a number of different patches. The 4 corners, the middle, that gives him 5, and then the left-right reflections of all those, that gives him 10. He runs all 10 through the network and then combines their opinions. In the top layers, where most of the parameters are, he uses a new regularization technique called dropout, which is very effective and stops the network overfitting. That's worth several % in his results. I'll describe dropout at some length in a later lecture, but for now the basic idea of dropout is that each time you present a training example, you omit half the hidden units from a layer. This means that the other hidden units in that layer, the survivors, can't rely on their comrades being present. They can't learn to fix up the errors left over by the other hidden units in that layer, because the other hidden units might not be there and they might be fixing up an error that doesn't exist. So they have to become more individualist. They have to individually do useful things. But they still have to do useful things that are different from what the other survivors do. So dropout is stopping too much cooperation between the hidden units. And a lot of cooperation is very good for fitting the training data, but if the test distribution is significantly different, then all that cooperation causes overfitting. Alex couldn't have done this work without significant hardware, but the hardware only costs a few $1,000s now. Alex is a very good programmer, and he used a very efficient implementation of convolutional neural nets on 2 NVIDIA GTX 580 graphics processors. Each of these has over 500 fast little cores, which are very good at doing arithmetic and not much good at anything else. The GPUs are very good at doing matrix-matrix multiplies. So if you stack together the vector of activities of a hidden layer over many training cases, that gives you a matrix, and now you multiply that by a matrix of weights to figure out the activities in the next hidden layer for all those training cases, and if both those matrices are big, the GPUs give you a huge advantage. They give you about a factor of 30. They also have very high bandwidth to memory, and that's needed for neural nets, because in neural nets you keep wanting to know another weight so that you can multiply by an activity, and there's millions of these weights, so you can't keep them all in the cache. Using all that hardware, he could train his final network in a week, and he could also combine results from 10 different patches at test time very quickly. So at test time, he can run at just about the frame rate. In future, we're going to be able to spread this kind of network over a large number of cores. As cores become cheaper, people at Google are already experimenting with that. And if we can communicate the states fast enough, we're going to be able to do much bigger networks on many more cores. Google has already simulated networks with 1.7 billion connections, and I think it's only going to get bigger. As the cores get cheaper and the datasets get bigger, these big, deep neural nets are going to improve much faster than the old-fashioned computer vision systems because they don't involve much hand engineering and they can make very good use of huge datasets and huge amounts of computation. So the fact that we've already opened up a big gap, I think means there's no looking back. I think from now on all the best object recognition systems, at least in static images, will use big deep neural nets. There are other application domains where we've learned the same lesson. So Vladimir Ni used a net with local fields, but without convolution, to extract roads from aerial images. These are cluttered aerial images of urban scenes. Again, he uses multiple layers of rectified linear units, and he takes a relatively large image patch and predicts for the central 16 by 16 pixels whether each of those pixels is a piece of road or not a piece of road. The nice thing about this task is that there's a lot of labelled training data available. That's because maps tell you where the centre lines of roads are, and roads are roughly fixed width. So from the vectors in the map that tell you where the centre line of the road is, you can estimate which pixels are probably road. Nevertheless, the task is very hard. There's the normal kind of vision problems, so roads are occluded by buildings because the plane isn't looking straight down when it takes the photograph. They're occluded by trees. They're also occluded by cars that are sitting on the road. There's shadow effects from buildings. There's major lighting changes, depending on whether it's a sunny day or a cloudy day, for example. And there's minor viewpoint changes. So the plane is basically looking downwards, but in any large photo it can't be looking straight downwards at every pixel. The worst problems in this data are the incorrect labels. You get incorrect labels because the maps aren't perfectly registered. For most purposes, you don't need a map to be registered better than a few meters. The pixels are about 1 meter square in this data, and so if the registration of the map is off by 3 meters, you're going to get at least 3 of the labels wrong for pixels across every road. Another severe problem is that the people making maps have to make arbitrary decisions about what counts as a road and what counts as a laneway. So in many of the maps, you look at something and you've no idea whether that's going to be considered to be a road or a laneway, and so you simply don't know what label it's going to get from the map. Big neural nets trained on big image patches, using millions of examples, are, I think, the only real hope for doing a good job of this task. It's very hard to find out what people can do. So here's what the data looks like. This is a part of Toronto. If you know Toronto, you can tell that by the angle of the roads. And above the image of the part of Toronto, I put 2 patches extracted from that image. And if you look at those patches, you can see it's not trivial to tell which the road pixels are. On the right is the output of Vladmir's system. Green is correctly identified pixels of road, and red means things that his system thought might be road that actually aren't. Actually, that thing is a parking lot, but you can see why he might have thought it was a road.